So here in example 2, we want to represent the net signed area under the curve f of x equals x minus 1 over the interval from 0 to -2 as the limit of a Riemann sum. Then we will write this as a definite integral for the area, use geometry to evaluate the integral, and then confirm our answer using the fundamental theorem of calculus part 1. So this is tying everything together. So first, I want to write it as a limit of a Riemann sum. So first, I need to figure out the base of each of my rectangles. It's going to be b minus a over n, or 2 over n. And then I know that my right-hand Riemann sum, x values, it's going to be a, which is 0, plus 2 over nk, or delta xk. So now, if I want to write this as an area, area equals the limit as n approaches infinity, the sum from k equals 1 to n. I'm going to plug this x value into the x value here, which is 2 over nk minus 1, multiplied by delta x, which is 2 over n. So there is my area as a limit. So now I need to write this as a definite integral. So this area equals the integral, well, we're going from 0 to 2, 0 to 2, oh, that's dying, of my function, which is x minus 1 dx. So now I want to evaluate this definite integral using geometry. So I can see that there are two triangles here. The height of this one is -1 and the base is 1. The height is 1 and the base is 1 here as well. So the area is going to be 1/2 times -1 times 1 plus 1/2 times 1 times 1. Those are my two areas of my triangles, which are opposites. So that area is 0 using geometry. So now I want to confirm my answer using the fundamental theorem of calculus part 1, which states that I can find the antiderivative of this definite integral, that's x squared over 2 minus x, and I'll evaluate that from 0 to 2. Plugging in 2, I have 4 over 2 minus 2, 2. And if I plug in 0, that's just getting 0. So 4 over 2 is 2 minus 2, which is 0. So we see the area under the curve can be written as a limit. It can be written as a definite integral. It can be evaluated using geometry and evaluating using antiderivatives.